So hello everyone. So in the last session I told that this the completion of this module. So we have one more topic left in this module, okay, that I did not discuss till now. So the last topic left in this module is discrete Fourier transforms, which are also known as DFTs, okay. Yeah. So what are these discrete Fourier transforms? Now let's discuss them. So the discrete Fourier transforms DFT convert a finite sequence of equally spaced samples into a same length sequence of equally spaced samples, which is a complex value function of frequency. Okay, so this is generally we consider this DFT in a general form, like it converts the finite sequence of equally spaced samples. For example, if in a sample the number of observations are 4 in a sample of natural numbers or some set of whole numbers or something, in that if there are 4 numbers in one set, so it converts the same set into the complex conjugate of the value, that is it converts it into the complex value. Okay, so this was all about discrete Fourier transform in generally. So now, based to this subject, we have the definition of this discrete Fourier transform, that is these DFT transforms a sequence of complex number which is determined by xk, and it is given by xk is equal to x capital X naught comma x1 up to x to the x to n minus 1, okay, which is defined by the formula given for this discrete Fourier transform is, so you need to remember this, xk capital Xk is equal to summation from small letter n tends to 0 to n minus 1, where here the capital N stands for number of observations and this n stands for the values, okay, where this n tends from 0 to infinity and this is the n minus 1. So this is given as xn into omega n into k, omega to the power n into k, where here omega stands for e to the power 2 pi iota to 2 pi I by n, where this I is called as iota or the imaginary term, okay, where this omega is also called as the nth root of unity. Okay, this omega can also be written as omega is equal to e to the power minus 2 pi I by n. Okay, it is one and the same. Okay, either you can write the omega as this or this, but in case of solving the problems, this is better. Okay, yeah. So wherever we have discrete Fourier transforms, in same way we also have its inverse discrete Fourier transform, and this inverse DFT is given by small letter x power n, x to n, that is this term. When you take inverse, right, let this be in one side, then all the other side will these terms will go to the other side. That is when we find the inverse of DFT, this x power n would be equal to 1 by n, where n stands for number of observation in the question, into summation from k tending to 0 to n minus 1, where n again are the number of observation, into capital of xk into omega to the power minus n into k. Okay, yeah, where again omega stands for e to the power 2 pi iota by n, where this iota or I is an imaginary term. Okay, this can also be written as minus 2 pi iota by n. Yeah, so these were all about the discrete Fourier transforms. Okay, so now we will solve one problem. It's very easy. Okay, you just need to understand the concept, and while solving the problem you will be very clear with the concept, because this concept is very important and it might come for the exam as well. That's why I am doing this. Yeah, so we'll solve one problem. Yeah, so this is the question. So the question goes like this: we need to find the DFT of sequence 3, 4, 5, 5. This is the sequence given. Also, we need to find its inverse DFT obtained from the signal. So, first we need to find the discrete Fourier transform of the signal given. After that, whatever the answer we got, right, using that we need to find its inverse discrete Fourier transform. So, can anybody tell me what would be the inverse discrete Fourier transform that we should be getting? So, the inverse Fourier transform that we should be getting is this itself. Okay. So after whatever we got the answer while solving the discrete Fourier transform, when doing the inverse, the resulting answer we should get is this set. Okay, if we do not get this set, then we have done the mistake. Okay, yeah, so now we'll solve this. So first this sequence is given, right? So this sequence corresponds to small letter xn, 3, 4, 5, 5. So where the values of there are 4 values given, so we can write the observations, number of observations as n is equal to 4. Also this set is of xn, right? So we can write that this is x0, this is x1, this is x2, and this is x3. Okay, if you want you can write it here separately. x0 is equal to 3, x1 is equal to 4, x2 is equal to 5, and x3 is equal to 5. So now the formula given to find out the DFT, we know that it is capital letter Xk is equal to summation for n tending to 0 to n minus 1 xn into omega to the power nk, right? So here we need to find first we need to find the value of omega. Okay, let's do that first. We know that omega given in the formula is e to the power 2 pi I by n, but the value of n given in this question is 4. So substitute that omega is equal to e to the power 2 pi I by 4. We cancel this 2 1s are 2 2s are, the remaining is e to the power pi I by 2. So this is again of the form e to the power I theta, right? And e to the power I theta is given as cos theta plus I sin theta. Okay, so here in the place of theta we have pi by 2. So what is the resulting we are getting here? Cos pi by 2 plus I sin pi by 2. So now substitute the value of cos pi by 2. You know cos pi by 2 is 0 plus I into sin pi by 2 is 1. So we are getting the final value of omega is equal to iota I, right? So now we need to substitute this omega value in this equation, that is equal to summation n tending to 0 to n minus 1. The value of n here is 4, so 4 minus 1 xn into the value of omega we got is I to the power n into k. Okay, yeah, so now we need to solve this. Xk is equal to summation of n tending to 0 to 4 minus 1 is 3 xn I to the power n k. So this is our general equation. So now in this we need to put the values for k as 0, 1, 2, 3 to find the discrete Fourier transform. Okay, so since there are 4 values given, so we need to substitute the value of k 4 times starting from 0. So now first we need to put the value of k is equal to 0 to find x naught. Okay, if you put k is equal to 0, the corresponding value here is x naught, right? So x naught is equal to summation n tending to 0 to 4 minus 1 is 3 xn into I to the power n into 0, right? The value of k is now 0, so x naught is equal to summation n tending to 0 to 3 xn I to the power n into 0 is 0, and anything to the base to the power 0, we know that it is equal to 1. So now finally we get the value of x naught is equal to, now so now remove the summation. We know that the value of n tends from 0 to 3. So now we need to, after removing the summation, we get it as xn into 1, that is equal to xn. So we get it as xn. So first we need to put x naught plus x1 plus x2 up to x3. The value of n tends from 0 to 3, right? So now we know that directly in the question only itself they have given the values for x0, x1, x2 and x3. So now substitute them. 3 plus 4 plus 5 plus 5. So while adding them we will get the first value of x0, that is 5 plus 5 is 10, 10 plus 4 14, 14 plus 3 17. See, the first value of x0 we have got by putting the value of k equal to 0. So now again put k is equal to 1 now. So now when we put k is equal to 1, the corresponding value we get is for x1 summation n tending from 0 to 4 minus 1, that is 3 again, xn, omega value is I to the power n into now the k value is 1. So x1 is equal to summation n tending from 0 to 3 xn into I to the power n into 1 is equal to n. So now remove the summation, so the corresponding set we get it as x, first value is x0, right, 0 to 3, right, x0 into I to the power 0 plus x1 I to the power 1 plus x2 I square plus x3 I cube, right. So now we need to solve this. I to the power 0 is a 1, right, so x0 into 1 is equal to x0 plus x1 into I plus x2 I square plus x3 I cube. So now we know that the value of I square is equal to minus 1, right, and also we can write I cube as I square into I. So again we know that here the value of I square is minus 1 into I, so the corresponding value of I cube we get is equal to minus I. So now let's write them here. So x0 plus x1 I, so I square is minus 1, so now x2, this x2 would become minus x2, right, and again the value of I cube is minus I, so minus x3 into I, right. So now again same thing, we need to substitute the values for x0, x1, x2 and x3. The value of x0 is 3 plus 4i minus 5 minus 5i. So the value of x1 we get is, first add the numbers, 3 minus 5 is minus 2, minus 4i minus 5i is equal to minus I. So this is the value we got for x1. So similarly put the values for k is equal to 2 and 3, then find the values for x2 and x3. So now put the value of k is equal to 3, so the corresponding value we need to find is for x3. Again it is summation n tending to 0 to n minus 1, that is 3 xn into I to the power n into 3. Okay, yeah, so I've skipped the k is equal to 2, I've skipped it. After this I'm going to do it. Okay, yeah, x3 is equal to n is equal to 0 to 3 xn into I to the power 3n. Okay, so the same thing again, remove the summation, first value is n is equal to 0, I to the power 3 into 0 plus x1 I to the power 3 into 1 plus x2 I to the power 3 into 2 plus x3 I to the power 3 into 3. So now x3 we get is x0 into I to the power 0 plus x1 into I cube, 3 into 1 is 3, x2 into I to the power 6, 3 to the 6 plus x3 into I to the power 9. So now we need to make some substitutions, that is we know that I0 is equal to 1 and we can write I cube is equal to I square into I, where the value of I square is minus 1 into I. So I cube we can substitute it as a minus I. So similarly I to the power 6, I to the power 6 we can split it and write as I cube into I cube, that is again minus I into minus I. Minus I into minus I is again I square, and we know that I square is equal to minus 1. So we can write I to the power 6 as minus 1. Similarly I to the power 9 can be written as I to the power 6 into I to the power 3, right? Yeah, so again I to the power 9, I to the power 6 is minus 1, and I cube we got it as minus I, so I to the power 9 it corresponds to plus I. Okay, so these values we can substitute in this. equations. So now x to the power 3 can be written as I to the power 0 is 1, so x naught remains, plus x1 into value of I cube is minus I, plus x2 into I to the power 6 is minus 1, plus x3 into I to the power 9 is equal to I. Okay, so now the same thing, x naught minus x1 I minus x2 plus x3 I. So now substitute the values for x1 naught, x1, x2 and x3. x naught is 3 minus 4i minus 5 plus 5. So x3 which we are getting here is now 3 minus 5 is minus 2, minus 4 plus 5 is equal to plus 1, so minus 2 plus I. So this here we got the values for x3. So now we have left with the left x putting k is equal to 2, right? So now we will do that. Okay, so we didn't find the value for x2. First we will find that. Actually first we needed to find this, after that this, so I've skipped that, so I'm doing it again. So n equal to 0 to 3 xn into I to the power 2n right now. So x2 is equal to, remove the summation, x0 into I to the power 2 into 0 plus x1 I to the power 2 into 1 plus x2 I to the power 2 into 2 plus x3 I to the power 2 into 3. Okay, so now substitute the values. This is I to the power 0 plus x1 into I, 2 ones are 2, so I square, x2 into I to the power 4, 2 to the 4, x3 into I to the power 6. So again now we know that I naught I to the power 0 is equal to 1, so this is equal to x naught plus x1 into I square is minus 1. So now we know that I to the power 6 we have found it here, that is minus 1. See, we don't know I to the power 4, so we can write I to the power 4 as I square into I square, right? I to the power 4 is equal to minus 1, I square is minus 1 into minus 1, so I to the power 4 which we get is equal to 1. Okay, yeah, so x2 into 1 plus x3 into minus 1, so x0 minus x1 plus x2 minus x3. So now substitute the values for x0, x1, x2 and x3. 3 minus 4 plus 5 minus 5. So the value of x2 which we are getting is now 3 minus 4 is minus 1, minus 1 plus 5 is plus 4, and 4 minus 5 is minus 1. So now we have found the values for x0, x1, x2 and x3. So now we'll write the discrete Fourier transform sequence, that is we needed to find capital X to the power k, right, which is equal to x0, x1, x2, x3. So the final sequence which you are getting here is, what is the value of x0? 17, x1 minus 2 minus I, x2 is minus 1 and x3 is minus 2 plus I. So this is your required discrete Fourier transform sequence. So now using this, where this corresponds to x0, this is x1, this is x2 and this is x3, right? So using this, now we need to find the inverse of this sequence. Okay, inverse discrete Fourier transform. We should remember that after doing the inverse discrete Fourier transform, the answer we should be getting here should be the same as the given question, that is 3, 4, 5, 5. Okay, so the inverse of this Fourier transform would be giving the answer that only. Okay, yeah. So now using this sequence, we need to apply the inverse discrete Fourier transform. Yeah. So now we know that in order to find the inverse discrete Fourier transform, the formula given is small letter xn 1 by n where value of n here is 4. Summation of k now, k tending from 0 to n minus 1, capital Xk, where the value of omega is I to the power minus nk now. Okay, yeah. So the same thing again we are going to apply it again. Xn is equal to 1 by the value of n is 4, summation of k equal to 0 to 4 minus 1 is 3, xk minus nk. So now first we need to put the value of n now, n is equal to 0 to find x naught. Okay, to find x naught, but we know that in the question we have already derived that the values of x naught, x1, x2 and x3 are 3, 4, 5 and 5. We need to get these values only as the answers. Okay, so now let's check that we are getting that or not. So first for x naught formula is the same, 1 by 4, k is from 0 to 3. So now the value of this becomes 0, right? Capital X naught, capital Xk into I to the power minus n into the value of k now is 0, right? So now we need to remove this summation, that is x naught is equal to 1 by 4 into, so now substitute the value of k from 0 to 3, that is this we know that I to the power n into 0 is I to the power 0, that is equal to 1. So the left out term here is 1 by 4 summation k tending from 0 to 3 x k. Okay, so now while we substitute we get it as x naught, the values of k is from 0 to 3, so x naught plus x1 plus x2 plus x3. Okay, yeah. So now x1 by 4 plus, substitute the values for x naught, x1, x2 and x3, that is 17 plus minus 2 minus I plus of minus 1 plus the value of x3 is minus 2 plus 7. So now simplify this, 17 minus 2 minus I minus 1 minus 2 plus I. So we can see that this minus I plus I gets cancelled. So x naught is equal to 1 by 4 into, add these terms, 17 minus 2 is 15, 15 minus 1 is 14 and 14 minus 2 is 12. So again 4 1s are 4 3s are. See, we are getting the value of x naught as 3. Correct, right? The value of x naught is 3 only, right? Yeah. So now put n is equal to 1 and find the other values, that is x1 is equal to 1 by 4 from k tending from 0 to 3, xk I to the power minus n into 1 right now. Okay, so x1 would be 1 by 4 k tending from 0 to 3 xk into I to the power minus n, n into 1 is n, right? So x1 is equal to 1 by 4 into, so take this summation sign, that is x naught I to the power minus 0 plus x1 I to the power minus 1 plus x2 plus x3 I to the power minus 3. Okay, so this x1 is now 1 by 4 into, so again I to the power minus 0 is 1 only now, so x naught plus x1, bring I to the power minus 1, bring to the denominator, so it will be x1 by I plus x2 by I square plus x3 by I cube. Okay, 1 by 4 x naught, so here plus x1 by I, keep it as it is. So we know that I square is minus 1, so if it is minus 1, so now this would become x2, right? Minus, this plus sign will change to minus since I square is minus 1, minus x3 by I, because I cube is I square into I and we know that I square is minus 1, so this sign changes to minus. Okay, yeah. So now substitute the values for x0, x1, x2 and x3 again. x naught is 17 plus minus 2 minus 2y by I minus of minus 1, right, minus 2 plus I by I. Yeah, so now we need to solve this. So we know that in these two terms the denominator here is I, so we can make this denominator I square so that we can eliminate this, right? We know that I square is minus 1. So in order to make this denominator I square, we need to if we do this as I square, we need to multiply the numerators by I, okay, for these two terms, okay, so that we can substitute the value of I square as minus 1 and this denominator goes. Yeah, so now we are going to doing that only now. 1 by 4, multiply numerator and denominator by I for this term and this term. So now if we multiply numerator by I, this would become I square, and I square is minus 1, so this plus sign changes to minus now. So minus 2y minus I square, right? Minus into minus is plus 1, and this sign changes to plus since the denominator I square, minus 2I plus I square. Okay, so now we are going to simplify this. So now x1 would be 1 by 4 into 17. There is a minus sign outside, so minus into minus is plus 2y plus I square plus 1 again minus 2y plus I square. So we know that I square is minus 1, substitute that. 17 plus 2I minus 1 plus 1 minus 2I minus 1. So plus 2I minus 2I gets cancelled. x1 is equal to 1 by 4 into, so minus 1 plus 1 goes, so 17 minus 1 is 16. So that is 4 1s are 4 4s are. So see, we got the value of x1 is equal to 4, right? So now in the same way we are going to find x2 and x3. Yeah, so I have substitute the value of n as 2. If we substitute n as 2, we get it as I to the power minus 2n. Sorry, this is minus 2k, okay? So here also this is k, okay? Since the limit summing is from k, right? Yeah, so this is k, okay? Yeah, so x2 would be 1 by 4. So now remove the summation. Now it will be x naught I to the power minus 2 into 0 is 0 plus x1 I to the power minus 2 into 1 is minus 2 plus x2 I to the power minus 4, right? I to the power minus 6. So now x2 would be 1 by 4 into I to the power 0 is 1, so x naught plus x1 by I square. So I bring this to the denominator, x2 by I to the power 4 plus x3 by I to the power 6. x2 is equal to 1 by 4 into x naught, I square is minus 1, so this sign changes to minus 1, and I to the power 4 is I square into I square, that is minus 1 into minus 1 is again plus 1, so this remains as it is. I to the power 6 is again minus 1, so this would be minus x3. So now again substitute the values for x0, x1, x2 and x3. x0 is 17 minus of minus 2 minus I plus minus 1 minus of minus 2 plus I. So now solve. So multiply this minus, so minus into minus plus 2 plus I minus 1 plus 2 minus I. Plus I minus I goes 1 by 4 into 17 plus 2 is 19 plus 2 21 minus 1 is 20. 4 1s are 4 5s are. So the value of x2 we are getting here is 5. Similarly find x3. Yeah, so now we find x3. I substitute the value of n as 3. So in the place of n it is now 3k. So remove the summation. I have written 0 minus 3 minus 6 minus 9. So now x3 is equal to 1 by 4 into I to the power 0 is 1, x1 by I cube plus x2 by I to the power 6 plus x3 by I to the power 9. Okay, 1 by 4 into x naught. I cube is I square into I, and I square is minus 1, so this would be now minus x1 by I plus I to the power 6 is again minus 1, so this would be minus x2, and I to the power 9 is I to the power 6 into I cube, that is minus 1 into, that is equal to minus I. Minus 1 into minus I, that's equal to plus I, though the value of I to the power 9 is plus I, so this would be x3 only. Yeah, I to the power 9 we are getting it as plus I, so plus x3 by I. So now the same thing again, here I and I are there, so substitute the value of x1, x3 and multiply the numerator and denominator by I square, so that we can cancel them out. Yeah, so here multiply the numerator and denominator in these terms by I, 17, so this becomes I square, the sign changes to plus, minus 2I minus I square, minus into minus is plus 1, again this changes to minus, minus 2I plus I square, so x3 will be 1 by 4 into 17 minus 2I and minus I square plus 1 plus 2I minus I square, so minus 2I plus 2I gets cancelled, 1 by 4 into 17, and the value of I square is minus 1, so this is minus I square, so it becomes plus 1, and again this is again plus 1, right? 1 by 4 into 17 plus 1 plus 1, that is equal to 20, 4 1s are 4 5s, again the value of x3 we are getting it as 5. So the inverse discrete Fourier transform sequence is for x to the power n, that corresponds to x0, x1, x2, x3. So the final answer for x to the power n we are getting it as 3, 4, 5, 5. It is a given question itself, right? So this is your inverse discrete Fourier transform. Okay. So in this way we are going to solve these kind of problems of discrete Fourier transform. The problem is lengthy, but the steps are very easy. You need to know the steps very carefully. Okay. So yeah, in this one problem I have told you how to solve discrete transforms along with the inverse. Okay. Yeah, so that's all. Thank you.